So the other day I was working on a project for a course, and I tried to program the solution for it. And I was using functional programming, which is the same type of programming you see me use in regular videos. And it turned out that the code I was writing became very cumbersome, and I had a lot of code. And I realized, I need to do something different. I need to use object-oriented programming. Now, for simple problems, and I call them simple, but they really are simple, like the ones I deal with on this channel, functional programming is typically sufficient to solve them. I don't need to write a whole bunch of code. I don't need to deal with a whole bunch of data, consider a whole bunch of different cases, organize things very neatly. I'm usually solving like one thing, getting an answer, plotting it, and that's fine. But in a research setting or in a true setting where you're trying to find something novel, you typically have to deal with a lot of different things, and people ask you, okay, give me this, give me this, give me this. And it becomes very cumbersome very quickly if you're using functional programming. Object-oriented programming is a very different way at looking at problems, and we'll get into that in this video right now. So obviously the main focus of this video is going to be on classes and object-oriented programming, but I'll use some of these libraries for some of the examples that we'll use, so I'll just import them here. So this video was separated into beginner, intermediate, and advanced, and I would suggest watching each section in order as they'll be in the video. And when you understand one and you sort of go through it and you play with the code a little bit, once you sort of get a grasp of what's going on, then go on to the next section. So for the beginner, I should probably just introduce what a class is in Python. The notation to define a class is like an object. It's like something in real life. And when you consider an object like a noun, there's that thing, and part of that thing, it has characteristics, right? So I could ask you, what's a rock? Well, a rock has a color that's gray. A rock has a size that's a certain size. It has a volume. It has a weight. It has a density or whatever. And so an object in real life has all these characteristics to it that make up that object. And that's sort of the whole purpose of object-oriented programming. Think of that term, object-oriented. The way that you think about problems is the way that you sort of think about objects. You have a thing that has attributes, and you can change those attributes. You can make the rock bigger, make the rock smaller, make the rock heavier, and then all these little things that you can change. And all the problems that you solve that are complicated in a research setting, you would deal with in that sort of way. So let's get into it. So a particle here. And I'm just considering some particle in space that has a position, it has a mass. Well, we define a mass. It has a velocity. So a very simple class. So you define your class. This is like my object. Now, when you create an instance of a class, for example, there's the rock, but there's a particular example of rocks. Then when you initiate that, you need a initialize function. So this underscore, init, underscore, that's the thing that gets called when you create the class. And you'll see what I mean in a second. And it sort of might seem abstract right now, but that's fine. So particle is the name of the class. And then a class has a bunch of functions inside it that either modify the class, create the class, or sort of return things about the class. So you'll notice this self keyword that always refers to the object. It's a word of referring to like you're within the class here. And self means like the particular instance of the class. And it's just something you get used to when you're dealing with this. So every function inside a class takes in the self keyword. So when you initialize, it also takes in the position, the velocity, and the mass. And then you say, well, self.x. So you always do self dot. That means you're giving attributes to that class. So x is just some random thing floating around in Python until the initialize function where it says, okay, this self.x means this attribute x of myself is this thing that I fed into the function. Same with y, z, v, x, y, and z, and then m. So I've defined all the attributes of the class, all these things that have been taken in that are just Python variables. They're now set as things about that class. And so ignoring sort of the other functions right now, you create an instance of the class that you name a certain thing. So I can define like P1 as a particle, and you don't worry about this when you initialize the function. You just worry about these arguments here. So I'm saying I'm creating a particle. The name of that is called P1, and I'm giving it x, y equals 0, z equals 1, vx equals 1, Vy and Vz are both equal to 0, and then mass is 3. So now I have one particle. And I can create many instances of a class, right? I can create another particle, for example, P2. And maybe it has like x equals 1 and z equals 0, and the same thing, other things. So there's this sort of abstract thing like, I have a particle. There can be a bunch of different particles, and each different particle has different characteristics. And that's what I'm saying with P1 and P2. They're different particles. They have different characteristics. So that's how you create an instance of the class. So it's used when I call this particle 001, blah, 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 all this. What's being called here is this function, this init function with all these arguments, and it's setting all the attributes of the class. And these attributes of the class, like .x, .y, .z, .vx, .vy, .vz, you can access them outside of the class too. So I can look at like p1.x. That's whatever was set to self.x within the class. That's, p1, the instance of the class. We can access that using .x. So think of like self.x inside the class thing. It's referring to itself. And then outside the class, this is like an attribute of the class. So p1.x, 0, because I gave it 0. If I gave it x equals 3, it would return 3. So it's setting all the attributes of that object that we created. So I also have some functions here that modify things about that object. And that's, of course, where object-oriented programming is useful. You could define an object that has a bunch of characteristics, but really what you need to do is modify those. And that's how classes sort of work with each other. And when you have big, complicated problems, it's these functions that really are the workhorse of what's going on. So, this move function, right, takes in itself, all functions take in self, and it takes in some time. And all it's saying is I know what the velocity is, I know what the position is, if there's no forces acting on it, my new position, self.x, it gets modified. So plus equals means like self.x equals self.x plus self.vx times t. So you're sort of changing the position of the particle. The velocity times time, that's just what, change is. So it's, I'm accumulating my original self.x equals self.x plus vx times t. If you don't know what I mean, this is just equivalent to this. Plus equals means take yourself and then add this other thing. And so this changes attributes of the class. So I can create my P1 particle like this, and then I can move the particle. So I know that it has a velocity in the x direction, right, vx. And I'm initializing vx, right, xyz is 3, 0, 1, and then vx is equal to 1. So it should move. When I call move, it should change the value of x. So I'm going to move for 2 seconds, t equals 2. So it should equal to 3 plus 1 times 2. So it should equal to 5 once I move this. So I move it 2, and then I can look at p1.x again. And sure enough, it's 5. So it's successfully modified the attributes of the class. So that's how you would set attributes of the class like this and then modify them using some function like move. And of course, there's many other ways that you could modify things of the class. Note that this function does not return anything, and this function also does not return anything. But there can be functions that return information about a particular instance. In this case, we call P1 the instance of our class. The class is called particle. Note the capital letter here, the instance P1. So everything, there's a lot of organization stuff that I'm sort of defining here, and it's used to sort of, think about what's going on there. Maybe create a few classes of your own. But this function here, get distance from origin, it takes itself and it, uses the attributes that it has, and it actually returns something. And it doesn't change anything about the class. It doesn't do whatever, but it just returns, in this case, there is no, there's self.z. And so it just returns the distance from the origin. Self.x squared plus y squared plus z squared square root. That's just the distance from the origin. So it's a function that doesn't modify anything about the class, but gives us some interesting information about that instance of the class. So I can call this function, and it will return whatever the distance from the origin is. And then, of course, like I said before, you can look at attributes of the particular instance. So there's attributes of the instance. Our instance of the class is P1. It's a particular particle that we defined of the abstract sort of concept, which we call particle. So P1, it has its own attributes, and I can look at X, and I, get this position here. So that's sort of everything about the, beginning of classes. So I would say still in the beginner section here, it's good to talk about inheritance of classes, because this is, again, something that's used all the time in programming. I mean, say someone defines this big class with all these functions and all this crazy stuff, and it works for everything that you want to do, but there's one part of the class that you want to change. And you could ask, well, do I copy all the code? Change that thing, it's a lot of code reborrowing. Maybe you copy something wrong and maybe they update the class or whatever. Well, the easiest way to do this is through inheritance. You inherit, think about what happens when someone inherits their traits, like from your parent. This isn't quite how it works, but it's a good analogy. Imagine you inherit all the traits of your parent and then you have a few additional things yourself. I know that's not how this works in real life, but that's sort of what you need to think about for programming. That's for some reason why they use the word. So a class inherits from another class if it has all the things about the class before it, plus maybe either you changed something or you added something new. That's sort of what inheritance is. So that's abstract, but let's think about what this means. So imagine in real life, you have a proton. That's a particular type of particle, right? But a proton also has its own special things about it. It's not just, its own particle. It's got all the characteristics of a particle. It's got position, velocity, mass, all those other things. But it has some unique traits that make it separate from a particle. It's got, its own things. It has charge. It has, spin, all these little things that a proton, for example, has. And so that's what class inheritance allows us to play with. So this is a definition of terms. We say that a child class, which is the proton, is the child of the parent. The parent is the particle. So proton gets all the things that a particle has, plus has its own little things as well. And the child can also have separate traits from its parents. So this is how inheritance works. So we're going to make a proton. I don't want to redefine all this stuff, this move and this get distance from origin in a new class. I want to save all these functions plus add a little bit. And so that's what we do here. So to define a proton, it inherits from its parent. So here we didn't have anything here. It doesn't inherit from anything. But here, the proton, it inherits everything that the particle class has. And then we define a new way to initialize this class. So the way we're going to initialize it is, same way that you initialize the particle. So it's got x, y, z, vx, vy, vz. We're also going to give it its charge. This is the charge of the proton in coulombs and the mass in kilograms. So we're adding some other things, right? And then instead of, recopying all this stuff from the init function, again, it's not very big here, but when you're dealing with big research problems, it is big. Instead of doing all that, copying it, you do this sort of weird thing and you just get used to it. You just use this code over and over. It looks weird. So what you say is you call the superclass. So that's kind of like the parent class. The parent class is the superclass. The superclass of proton, and then self, you always use self here. So this is just notation. You just use this. So super. So it's going to call the init function of the superclass. So what is that function? Well, that function is this function here, right? So it's going to call that. And it's going to, set all those traits like that. And so it's going to call that init function, and it's going to take in all the arguments that we've sort of taken in here and the mass. So then the proton not only has the init function of the particle, which is called here, but it gets these additional traits of Q and M when you initialize the photon. So then we got the photon class. We can give it initial position and, well, I have to define it first. Initial position and velocity. We can, we haven't defined move here, but it's inherited move from here. So it's got that function from the particle class. So we can, like with the particle, we can move the proton and see where x changes. So x started at 0, but it's got velocity in the x direction. We move for 2 seconds. 2 times 1 second, you get 2 meters or whatever. So 0 plus 2, and you get, the new distance here. Now, like I said, you can also give the child additional traits from its parent, right? So a proton has the electric charge, but when you move the proton, maybe you're in an electric field and it's a charged particle, in which case the movement of the particle, of course, is going to depend on the electric field, which applies a force to that particle. So we can redefine the move function. We're actually changing the move function of the particle. And so what I do here is, okay, so this is just kind of like above, but now I'm redefining the move function, right? So I have the old move function, but I'm going to redefine it here. And so now my distance is v times t, but also the electric field causes an acceleration of the particle. And the acceleration is 1/2 q over m times ex times t squared. That's just a result of constant acceleration of particles. And you have the same thing for ey and ez. The move function now also takes in the components of the electric field. So we're changing the move function from what it used to be for a particle. Now it's a little bit more specific for a proton. And then the velocities, of course, also change. So you also have to update the velocities here. Then we can add new things. Maybe we want some more stuff that we want to get from the proton. So I define this new function called get position. So the particle doesn't have this, but maybe for some reason I want this for the proton. So it returns sort of a 3 vector of x, y, and z. And then maybe also something we want velocity. So it returns vx, vy, vz. Now, I'll take a little break here and note that, it's very easy when you're coding class stuff to forget the self keyword. Maybe you just use q over m times ex times t squared. You have to remember this. It can cause a lot of bugs if you forget to use self dot whatever. So you're always changing the traits of the class. You have to think of it that way. So, self dot x, I'm changing the x trait of the class. Using the velocity trait of the class. Time is just something I feed into this function. And then it depends on the Q trait of the class and the mass trait of the class. And so everything here is about changing attributes of the class, calling this function. So always remember the self keyword. And again, in functions too, always remember the self keyword. Here I'm returning traits of the class, self.x, y, and z, which are defined when I call this init function. And so, okay, so now I have this new proton class with some additional stuff. So again, I can define it like before. Now I can move the proton, but here I specify an actual electric field. And then I can get the position of the proton from that electric field. There's a mistake, by the way, here. I mean, I call myself a physicist. Maybe this is wrong. Like, I'm pretty sure this is right, but, correct me if I'm wrong. I'll add a comment to the video. I think this is what the motion of a charged particle is in a field, but I make mistakes. So we move the particle like this, but then we can change the attributes again. Maybe we want to move the proton some more. So then we can move it again with, maybe we give it a different electric field for 3 seconds. Right? Then we get the position of the particle like this. So the idea here is that we define the class, we give it its traits. We have these functions that then modify the traits of the class. And then we can get information about that class. And so that's sort of the foundations, to some sense, of object-oriented programming. And, it makes sense for particles in here, and you might think, this is sort of a trivial example. But in the intermediate and advanced parts of this video, I'll talk a little bit more about where that really becomes a practical advantage. Okay, so for the intermediate portion, I want to focus on a particular physics problem. And that problem is projectile motion. No air friction, no nothing, just a particle traveling in a quadratic path through the air. So what, we need to consider there? Well, we need to give the initial xy position of the particle, the initial velocity of the particle, it's just 2D, and the time at which we want to consider sort of the path of the particle. So maybe we want to consider for 10 seconds or whatever. And that will give us information about the distance and the height and whatnot. And then maybe we want to get some additional properties for a particular motion. We want maybe the height, the maximum height reached, the horizontal distance, the sort of horizontal distance traveled as it reaches the ground, the time when the maximum height is reached. Actually, this get peak x is the horizontal distance corresponding to the max height. Get x landing returns the horizontal distance totally traveled by the particle when it reaches the ground. So we have all this stuff, we have a problem. And in object-oriented, when this would be useful is, well, maybe my research is I want to consider thousands of particles, right? So I can make thousands of R naughts, thousands of V naughts, thousands of T spans, get thousands of things here. So there's a lot of properties about a particular problem here, right? We have the initial conditions, we have the actual motion itself, we have the actual height and x, and it gets a little cumbersome to define all those arrays. Whereas a more organized way of doing this would be, I'm going to consider just a particle, and we have 1,000 different particles, and that's it. And we're going to consider all those things in a particular class. So each class would contain the initial conditions, the motion, the maximum height, all that stuff. And that's sort of what we'll do here. So we define this projectile class, like we did above for the particles. So what do I need to initialize this class? It's a projectile motion. Well, I'm going to give it the initial position, which is defined here. It's just xy. It's a tuple, two things. Initial velocity, the gravity, and the time span, which we're going to consider over. And so, of course, the first thing we sort of need to do is we call self.t, so that's the time attribute of the class. Then I just extract the x and y position and the x and y velocity initial conditions from r naught and v naught. Of course, it's an array that contains two values, or a list that contains two values. So I just extract them out of the list like that. Same thing with the velocities. And then I define my x and y. So these are all the x's and y's, so the discrete positions that it takes throughout the time span. So it's the initial x plus vx naught times t. This is just projectile motion stuff, right? So I've defined the position of the particle as a function of time throughout the motion. And that's what I want. So then I have functions that I can extract things about a particular particle. So here's get peak y, right? It takes itself, it just returns the maximum y value. So I have all my y's in an array, and this returns the maximum y value. Get peak x, of course, that'll return the x corresponding to the maximum y. So mp.argmax, that says, where is y maximized? I want that point, that integer of the array. So it's just the sort of place in the array where y is maximized. So this will return basically a number, the element of y that corresponds to the maximum value of y, and then I extract that value from x. That gives me the peak x. And I do the same thing for getting the time corresponding to the maximum height as well. Then there's a function here which gets the X landing position. So, you can look into this a little more. Explained really simply, there's the peak time that's sort of halfway during the flight, right? And so I only want to consider times that are greater than this time because it reaches the ground at the beginning and at the end. And so if I don't want to consider the beginning point where it reaches the ground, I'll take only the times at the second half of the motion. So I say, well, I want to get my X's and Y's. So this just returns two arrays that correspond to the bottom falling part of the motion. Again, you can sort of play around with this outside of a function. And then you can basically say, I want the value of X after the peak. So after it starts falling, I have my X's and Y's. And I want you to get the minimum value of Y, the closest value that Y is to 0. Because of course it'll go like this, and then it'll fall below Y equals 0. I want the value of X corresponding to where Y is closest to 0. And that gives me sort of the horizontal distance traveled. And so this is my projectile class. And I can run it. And then I can create a particular, instance of the projectile. So here I create a projectile called P with these initial conditions, this gravity, and this time span. So 100 times between 0 and 2. And it'll save all the corresponding X positions, like discretely, and all the Y positions discretely of that projectile. And then I can plot stuff. So for example, I know that there's the X and Y attribute of the projectile. So when I plot, I just call p.x and p.y, and it'll plot that. And I can put like a horizontal line at the peak Y position. So I'm calling this function, and I'm calling the peak X position as well. So the X corresponding to the max height. And so you can see I get this vertical line here corresponding to the peak X position of the flight and this peak Y position here. So I have my particle, I have all the stuff, and when I plot it, I can just call things from that particle as opposed to, defining each of them separately. And again, this is handy if I have a bunch of particles. Like I said, the real advantage is when you're dealing with many classes. So we'll sort of start like this. So suppose I have a bunch of different launch angles, theta, initial condition, initial launch, between 0 and pi over 2. And my speed that I'm launching it at is 5 meters per second. So I define my initial Vy's and Vx's just as arrays here, right? Like if I look at this and I define this, it just gives me a bunch of different initial X velocities and a bunch of different Y velocities. And I want to create a bunch of different classes, each with a different initial condition. So for that, I can use list comprehension, right? So here I have, list comprehension is something like this. So for example, I squared for I in range 5. Returns sort of a list like this. This is how list comprehension works. And I can do this for creating classes as well. So here I create a projectile. So that's like this part of the list comprehension. Projectile with Vx, Vy. So this is like I, right? The actual argument here. So Vx, Vy, G. The particular time span for Vx, Vy in, the zipped combination of Vx's and Vy's. So it creates a bunch of different projectiles, stores them in a list, and each of those projectiles has separate attributes. And then I can compute maximum heights and distances traveled for all those projectiles as well using list comprehension. So here I say I want you to get me the projectile's maximum Y for P, right, in all the projectiles. So these are my list of all the projectiles, and iterate through each one of them, P for P in P's. And so that gives me the maximum heights of all these projectiles. Same with the X landings. It says, for all P's, we call P the current sort of thing that we're going through, and we get the X landing. And then we get lists of maximum heights and X landings. And I can plot thetas here. There's going to be 100 different thetas. There's also going to be 100 different max heights. I can plot thetas and max heights. So you can see that, of course, the peak height occurs when I launch it at pi over 2. And then the X landings. And this is a fact of projectile motion. The largest X landing possible occurs at a launch angle of pi over 4 for no air friction. And so you can see that all that information is stored in the particles. But even then, you can make this simpler with an even more advanced class. And this is where object-oriented programming builds on itself. So now I'm going to create a class called projectiles with an S, multiple projectiles. So what it does is its attribute itself is that it has a bunch of different projectile instances inside it. So here I give it my initial position, and this projectiles class takes in a bunch of different initial velocity conditions. That's why I put the S after V naught. So it takes in a bunch of different V naughts, G, and then the same time span. So what it does is it creates a bunch of different instances of particles, and it calls them P's. So this projectiles That's your class now. That's your object, is a bunch of projectiles. And it says this attribute of mine called P's is a list of all the projectiles, right? So now it's got itself, this class has a bunch of different other classes as its attributes, right? Just like how I defined the projectiles here, this now becomes an attribute in my new class. Then if I want to get the maximum heights, X landings, and even just the list of the projectiles itself, here I just return the maximum height for all the things. So now, right, I have this projectiles plural class that itself has an attribute of a bunch of different projectile instances, right? So these are a bunch of different instances of the projectile class, right? And so I can define them like this. So I have my thetas. These are all the different initial conditions. Then I define all my different Vx's and Vys, which of course are going to be specified in this array here. So then I create an instance. I'm actually going to call this P's to avoid confusion. So P's is an instance of my projectiles class that has this initial condition, this initial velocity. So what I'm doing here, by the way, I have my Vx's and Vys like this. Oops. They're just arrays like this. Now if I call np.array Vx's, Vys, it sort of stores them like this. But if I transpose this, it gives me a bunch of different tuples. So Vx, Vy, a list of, okay, this is my next Vx, Vy, this is my next Vx, Vy, by transposing it as opposed to leaving it like this. And that's how I feed it in. So my V0s is an array of like, each row corresponds to separate initial conditions. That's why I define it like this. I have my gravity and my time span. So now I have my new instance of the projectiles class called P's. And I can get the X landings like this. I want the get X landings function called on this class here. And it will get me all my X landings. And then I can plot thetas versus X landings sort of like this. So here, this is all I've done here. I can delete this. This is all I've done. I get my X landings and I can plot. So there's a lot of stuff done very simply in my code here and here and here once I have that class defined above. And then of course I need this class defined as well. So this is where object-oriented programming starts to build on itself. So you can see that by defining this projectile class and the projectiles class, I don't need to write very much code here to, start examining things. And so what you would do typically in programming is you would stuff these classes in a separate file, import them. You don't have to deal with all this extra stuff in your notebook when, for example, you want to make plots for research or something. So that's kind of the idea with this. So finally, I'll go through sort of an advanced thing here. And it's kind of similar to the intermediate part, but it sort of builds on why this is important, this sort of object-oriented thing. And so, of course, in real life, a projectile experiences lots of different arbitrary forces acting on it. It could have gravity, air friction, electric or magnetic fields. Like there's infinite possibilities of the type of forces acting on it. So we're going to define a more advanced class that can take into account these factors. So we'll take into a force function, an arbitrary force function. It's a general force acting on a particle, and it will sort of encompass all different conditions. And if you want to see more about this, I'm not going to go a lot in depth in this video, but you can look at my projectile motion video. I didn't use classes here, but it sort of goes over the techniques I use to solve the differential equations, right? When you have a general force, you have to solve a differential equation to get the motion of a particle. So now I'm going to change my projectile class a little bit. So I initialize it, I still give it the same position, initial velocity, time. Now I'm giving it f, and f is a function, right? F is not a number or anything like that. F is actually a defined function. And then I'll show you that in a bit. And then mass, and then it can take in as many extra arguments as you need. Why does it do that? Well, these arguments might be needed for this force function. Maybe it's an electric field in the force, maybe it's a friction parameter or whatever. So I'm going to allow this class to take in as many additional arguments as it's needed. And I'll sort of set all these things like that. And then any additional arguments that are passed in get stored in this list of self.args. And so unlike before where I could just specify, right, up here, when I solve the motion of the particle, I just specified self.x, self.y equals whatever. And then I get my x's and my y's of the particle. But here I have to solve for the motion of the particle. So I can't specify x and y at the beginning. I have to have a function that solves this. So this function, I actually define a function inside this function. So again, this is where I'm using the technique from the projectile motion video. So I won't go into it in too much depth, but what it does is it takes a vector. If s is a vector of x, vx, y vy, it takes in that and it returns the derivative. And that's how you set up a system of differential equations. Again, if you want this in more depth, check out the projectile motion video. I'm just showing this as an example here, so don't worry if you don't understand it. And this function here inside this function, this is the function used to solve the equation. Then like in the projectile motion video, I use solve IVP. It takes in this ds dt. This function is a system of differential equations. That's what it is. So it takes in the system of differential equations, takes in the time span over which I want to solve for, takes in the initial conditions, takes in the times I want to solve over like at each point, and then takes in any additional arguments as well. And then I can find my x vx, y vy from the solution that's given here. And solution.y contains all that information. So again, if you don't understand this, don't worry, but it's a function I'm using to get the motion of the particle. And it's a separate sort of thing in this class. Then like before, I can use the same functions to get peak y, peak, the x corresponding to the maximum height, the time, and then also the x landing position. So everything here is the same. In fact, I could have inherited from that other projectile class. That could be a good exercise to look at, because all I'm doing is I'm doing the same things as the other projectile class, but I'm writing a new function to solve the motion. So you could think about using inheritance there with the old one. Now I have an arbitrary force. Now I can inherit from that class and do something like this. So here I have my new projectile class. And so now I can define these functions. I'll define force 1 and force 2. Force 1 is quadratic air friction. Force 2 is linear air friction. It just takes in all these parameters and returns the force in x and the force in y. That's exactly what I have here and here. So here you have, the friction force in x and then the friction force in y plus gravity, essentially. And you have the same thing here, but with quadratic air friction. So this force 1 and force 2, these like functions called force 1 and force 2, are fed in as the f parameter here. So it's got an attribute. The projectile has an attribute that is a function. It's not a number or whatever. It's an actual defined function. So self.f literally becomes force 1, which is a function. So now we'll set up our particles. We'll create one instance that experiences gravity and quadratic air friction, and I should have written linear air friction here. So now I have one that experiences gravity and linear air friction. So we'll set up these initial conditions for both particles, same with the initial velocity, times that I want to solve the differential equation over, and then I set up my two particles. So P1 is the particle that experiences force 1, and then these are the additional arguments that I give here. So args becomes gravity and the B1, which is related to the friction here. And then P2, which experiences the linear air friction. And then these are the additional arguments that are taken in. And then I call solve motion for both particles. And I can plot the motion of both particles. And I can use, like, for example, P1 to get peak x. Again, I'm not having to do all this stuff with arrays. It's all managed by the class. Very simple. So I put a dotted line at the x corresponding to the maximum height for both P1 and P2. And of course, this is comparing two particles that experience different frictions. So, the blue one experiences some sort of quadratic air friction. You can see they have the same path up, but the one that experiences quadratic friction sort of keeps going a little bit, and then the linear friction kind of directly falls off, even though they experience the same path going up. Of course, the frictions are very different. The thing to notice here is that these particles experience the same sort of thing here, and then they dramatically vary later on in motion. So quadratic and linear give different sort of results here for the motion of a particle. So that concludes this video. I didn't go too much into depth of what the actual things of the function are doing, but I hope it makes you realize how convenient object-oriented programming can be to store a bunch of information about something and then access it really easily, like here and here, without having to do a bunch of modifications. It's all managed by the class that you define. I put a little exercise here that you can read through. It sort of builds upon the stuff that we talked about in this video, defining other classes and using it to get information. And so if you want to sort of pursue that a little further, I would highly suggest looking at this as well. If you made it to the end, congratulations. Join the Discord server, like and subscribe, and I'll see you next time.